Thank you everybody for inviting me to this beautiful and very inspiring Biomedical Imaging School. So today my goal is to talk about AI for accelerated magnetic resonance imaging. But prior to diving into this field, so I'm going to give you a few introductory words and of course some educational aspects to allow you to fully understand the content of my presentations. So as Monique mentioned, I'm working at Neurospin, which is a unique facility for brain imaging and doing essentially MRI both in the preclinical setting and in the clinical setting, with the specificity of focusing on ultra-high magnetic fields from 7 Tesla to 17 Tesla in small animals, and from 3 Tesla to now 11.7 Tesla in human. And so why pushing the magnetic field strength so high? So the reason is first and foremost to increase the signal-to-noise ratio and avoid any noise in the images. And this is a nice illustration here in the human brain to show you the gain in signal-to-noise ratio, but also in contrast-to-noise ratio, which means your ability to distinguish the different tissue in the human brain, and in particular to differentiate white matter for gray matter. Of course, this is beneficial for morphological or anatomical imaging with this famous T2 star weighting imaging, which is a specificity of ultra-high field, but also for diffusion weighted imaging if you are interested in reconstructing the myelin fiber bundles, or in functional imaging if you want to do notably layer specifics or functional MRI. It's also advantageous to reach a gain in spectral resolution for spectroscopy. If you want to separate the peaks of neurotransmissions between different metabolites. So here is a typical now possible imagings we can do on non-human primates, for instance, but on the clinical scanner operating at 11.7 Tesla at Neurospin. So which means that soon we will be able to show you similar images for in vivo for the human brain. But as you can see in these acquisitions, so the acquisition time is almost 2 hours, which is not compatible with clinical investigations. Now, typically in the clinical setting, so we want to push the resolutions, the current resolutions from millimeter to mesoscales, meaning approximately 0.1 or 0.2 millimeter isotropic. So as of now, it's doable, I would say, in ex vivo imaging, but in vivo we know in the literature, the recent literature, that there has been some preliminary attempt to do that, notably with this work at Magdebourg on 2D T2 star weighted axial imaging with 120 micrometer in plane resolution and 600 micrometer as a slice thickness. But the problem is that it's, again, the scan time is long, 45 minutes. And of course, there is also the questions of handling the motion, so how to correct and mitigate the motion which induce some blurring artifacts. So we need techniques to accelerate, to speed up the acquisitions. There are two possible interesting topics for doing that. So either you reduce the scan time for a given resolution, for instance, to reduce the cost, to limit the patient discomfort, and to accelerate, to increase the patient's throughput as well in the hospitals, or to increase the resolution for a given scan time budget. And it's particularly interesting for functional MRI and other imaging modalities like diffusion, for instance. But here, today, we're interested in this first goal, so reducing the scan time for a given spatial resolution. So the agenda for today, because I need some backgrounds that I'm not sure you are all aware of, I will try to be pedagogical by reintroducing some background in MRI in the first part and moving to compressed sensing technique and what we have introduced as a sparkling technology to speed up the acquisitions. And we will see that with this part, okay, we can speed up the acquisitions, but basically we transfer the complexity from the acquisitions to the image reconstruction. And that's where machine learning, and especially deep learning, enters into the game to basically speed up and accelerate the image reconstruction task. And for that, because this is the first course of the summer school about AI, I will give you a brief introduction on supervised learning in particular. And then, if time permits, I will present you our last achievement that combines both techniques in a deep learning setting, so basically designing accelerated acquisition techniques with deep learning reconstruction strategies. Okay, so let's start with this refreshment on MRI acquisition and MRI principles. And thanks to André for already priming us in the previous talk about that. So in MRI, what kind of signals are acquired? So as you know, we are essentially doing imaging of the water, density of water, and how our H2 water molecules are composed of oxygen and hydrogen atoms, and the hydrogen atoms have specifically angular momentum, which basically translates into a magnetic momentum that can be represented as a small magnet. And of course, in every molecule, you have a different, in every, I would say, nuclei of hydrogen atom, you have this kind of small magnet, small spin that is randomly oriented, notably in this ambient space. So if we want to measure macroscopically these magnetizations, so what we do first is that we put the volunteers in the scanners, and these spins are aligned in the direction of the magnetic field, the B0. And now what's happening is that the spins will rotate at a given frequency, which is given by the Larmor frequency, which is proportional to the geomagnetic ratio specific to the hydrogen atom here for this value. And we have seen in the previous talk that by changing the targeted nuclei, we change the geometric ratio, and B0, of course, impacts the angular frequency, the frequency. And so the problem is that, okay, we can generate this magnetization, this global magnetization, but this magnetization is aligned with B0. So how to measure correctly this magnetization M0? Because we need to disentangle it from B0 itself. And to do that, we're gonna use a radio frequency pulse, basically specifically tailored at the same frequency to induce the famous nuclear magnetic resonance, okay? And by doing that, we induce an energy transfer, and we tip the magnetization in the orthogonal plane to induce this phenomenon. And when we stop this, the application of this RF pulse, what you observe is that, of course, you measure the return to the equilibrium, to the positions aligned with B0. And so you can observe that along the XY plane, notably in the transverse planes, the lifespan of the MR signal is very small. And that's why in MRI the acquisition is slow, because you need to repeat this process several times. So what you measure with the receiver coils is basically these damped sinusoidal signals, which is represented here, that you can demodulate because you know the Larmor frequency, and you obtain these free induction decay signals. Okay, but this is just a signal. This is not an image. So how to get an image? We'll see that in a minute. So these signals actually represent global and spatial integrations over either the slice excited or the volume excited with your radio frequency pulse. So this is basically a summation over the excited portion of the brain here, and you measure a single signals. So now we need an additional ingredients to make an image. And these ingredients relies on what we call the gradients that are used for spatial localizations. So we have 3 different gradients along the 3 different directions or dimensions. You have this illustration here and there. And how are we gonna use these gradients? So remember, we have these Larmor equations, and then what we're gonna do is to add actually linear gradients according to the different spatial dimensions. And by adding these gradients, we vary the Larmor frequency as a function of the positions. So basically, we established a one-to-one mapping between a Larmor frequency and a spatial positions. And by doing that, what's happened now is that each spatial localizations will have a different rotating speed and a different phase. And so if you integrate over time this phenomenon for a duration of t, you will end up with a phase called phi that writes like this. Still, this Larmor frequency, this carrier frequency, I would say, plus these modulations due to the spatial encoding. Okay, so we end up with the signals that writes like this. Now, okay, it's still an integral with respect to space. But now, by doing a bit of work and calling our friend Joseph Fourier, we can first denote KL of t as this integral with respect to each spatial axis, Lx, x, y, and z, and observe that finally the signal is nothing but the spatial Fourier transform of the original object. Okay, so basically what you are measuring in MRI is the Fourier transform of your object rho, of your density rho. This is an illustration in 3D, but of course, if you are doing a 2D excitations, it's only a 2D acquisitions and a 2D Fourier transform. So here is an illustration of what's happening. So this is what we call the K-space, representing in 3D Kx, Ky, and Kz, and basically showing you how to navigate in this spatial frequency domain during the acquisition stage. And you have, of course, a one-to-one mapping between this K-space and their temporal derivatives, the gradients that in practice you manipulate in your pulse sequence to tell to the MR systems how to collect the data, basically. So this gradient system have hardware specificities. We have seen in different imaging techniques, in PET, in optics, and so on, that we have hardware limits, and this is the same for MRI. In particular, 2 important hardware constraints are what we call the Gmax, the peak gradient strength, the maximum intensity of the gradients that we can apply during a certain amount of time. And then we have also the slew rate, which is typically the rise time at which speed we can commute from the downstate to the upstate. And the first constraint on the maximum gradient strength is called Gmax, will impact basically the speed of the trajectory in your K-space. So the function Kx, Ky, and so on. And you can see here that, for instance, the red curve is non-admissible because it turns too fast, it goes too fast. It doesn't fulfill the constraint which is written here, and which is a mixed norm between the L2 norm with respect to the derivative of the trajectory, and this has to be fulfilled at any time point. That's why you have a supremum over time with respect to all time instance. And then you have the second constraint, which is given by this speed of commutations. And now this is the derivative of the gradient itself, so the second derivative of the trajectory KL. And again, and this is a constraint on the accelerations this time, just to tell you that, for instance, you cannot basically collect data with really singularities like this, or angles at 90 degrees, unless you completely stop the systems, and in that case, you lose time. This is exactly the similarity with driving a car. Okay, you are driving a car in the Fourier space. You cannot make a very sharp turn at 200 kilometers per hour. It's impossible. So it's very kinematic. Understand this as a kinematic constraint. Okay. Now with that, the basic pulse sequence here, just again for the purpose of allowing you to understand how it works. So it's what we call a spin echo sequence, but it doesn't really matter. So here we apply a radio frequency pulse, so it's in 2D. I have only two gradients, what we call the readouts and the phase gradients. And we play with these two guys in a chronogram, in a pulse sequence, to collect the k-space. Remember, the trajectory here has a derivative of the gradients. And here it's a very simplest example. We're going to do exactly what Matthias talked about yesterday morning, the spin warp approach. Cartesian acquisitions, line by line, so very lengthy, very long in time. And so we do that, we repeat the process, and so on and so forth, and we fill up basically the Cartesian grid. And then, because we have done that, we have a full k-space, we can apply an inverse Fourier transform to gate an image. Okay, so it works. But it's pretty long. And the scan time to just collect these slides will be what we call the time of repetitions, which is basically the time intervals between the applications of two consecutive radio frequency pulses times the number of phase encodes. The number of phase encodes is the number of lines to collect this data. So, and this time collecting a line is often negligible as compared to TR. And the number of average, if we repeat multiple times the same acquisitions. Of course, usually we try to get this number equals to 1. So now, if we want to speed up the acquisitions, the most naive idea, of course, is to undersample this plane, this 2D acquisitions plane. And because I told you here that the most time-consuming aspect is these directions, okay, the number of phase encodes, we of course want to diminish the number of phase encoding steps. And if we do that naively, because there is a Shannon-Nyquist theory, we will end up with aliasing artifact along the undersampling directions. And why this happens? Just because here, the space between two consecutive lines is larger than 1 over the field of view. Okay, it's basically the transposition of the Shannon theorem into the dual space. You collect the data not in the time domain, but in the Fourier domain, and you apply the reciprocal criteria in the image domain. Okay, so, and this gets even worse if you increase your resolution, which means increasing resolution means making this square wider. Another solution that has been developed for 20 years, even more, is what we call parallel imaging. Basically, in the previous formulation, we ended up with less data than the number of unknown in the image space. So to circumvent this issue, we can collect complementary data according to multiple coils that are just sensitive to a portion of the organ, here the brain, but it works for any organ of interest in the human body, and make the complementarity between these two guys, you see, accumulate multiple data sets, and then it's just a least square problem to recombine the aliased image, but you have as many aliased images as the number of coils, and it's pretty easy to solve as long as the undersampling factor is lower than the number of coils. But here we are not interested in doing that. We are more interested in using more advanced techniques that can be combined with parallel imaging, like compressed sensing. So compressed sensing has been originally introduced in 2006 by two mathematical teams on the West Coast in the US. Dave Doono on the one side and Emmanuel Candes and his colleagues on the other side. And it relies on C complementary pillars. The first pillar is sparsity, and I will give you the idea of what it means, or compressibility. The second pillar is pseudo-random or incoherent sampling, and I will give you also an idea of what it means, and nonlinear reconstruction. So sparsity and compressibility. Sparsity means that basically you could represent your image by a few non-zero coefficients. So in MRI, the only case, to the best of my knowledge, I know where I can do that natively in the image space is angiography, because the image is almost dark, or almost zero everywhere, unless for the vasculature. Okay, but in general, our brain image is not sparse in the image domain. However, if you find a domain in which the transform representation of your image is almost zero everywhere, except in a few well-identified, for a few well-identified coefficients, then it works. And this is exactly what happens when you apply either wavelet decomposition, wavelet transform, or shearlet, or curvelet, and so on, all these type of multi-resolution analysis tools that come from harmonic analysis, or even if just you compute the gradient of the image. In the space of the gradients, where you compute the directional derivative of the image, you will see that at least it works for piecewise constant images, but it works for a lot of natural images as well. You will have a few, only a few non-zero coefficients. And here is an example of the wavelet decomposition of this image, where you can see that the image is not exactly sparse, but it's highly compressible, which means that you see only a few white pixels, and most of them are black. And to give you a more intuitive idea of what's happening is that here is the original image, and if you if you compute the wavelet transform, and then you keep only the 10% of the most significant coefficient in this wavelet domain, and then you hard threshold these coefficients, you put the other to 0, and you go back to the original image space, you see there is almost no difference between these two guys, which means that this image is highly compressible. And we will rely on that concept to accelerate the acquisition in the end. You can reproduce this game with a higher acceleration factor, and of course, at some points, you will degrade the image quality because you lose information contained in the image. But in compressed sensing, we don't use this compression proportion to limit the storage, but more to accelerate, in the interest of speed, to accelerate the acquisition. And how we do that, basically the underlying idea is that if you can represent your image with fewer unknowns, then you will need fewer measurements at the data collection stage, and so faster imaging. There is an empirical rule of thumb which tells you that you need 2 to 5 measurements for every sparse point in your representations. And acceleration factor is directly linked to the sparsity, so I won't go into details, but in the theoretical literature, you can show that the number of measurements to get a very exact recovery of your image, the number of measurements needs to satisfy this inequality, where S is the degree of sparsity, so the number of non-zero coefficients in your image, times the logarithm of the image dimension, times the constant. Anyway, the second ingredient is what we called incoherent sampling. So here I won't go into details to save time, but what I'm going to tell you is that incoherent sampling means basically just imagine, so you have your sinusoidal case, so you have just a sinusoid which is represented as just a frequency peak in the frequency space. And of course, if you project back into the time domain for 1D signals, then you get back a sinusoid. Making an incoherent sampling will basically consist in as much as you can randomly undersampling your signals, okay, to avoid the artifacts we obtain by doing a regular and deterministic undersampling we observe with the Nyquist criteria. So we're going to try to spread the measurements we collect to limit the artifacts at the reconstruction stage. And basically, a key tool to do that is to implement pseudo-random undersampling in the acquisition space. And of course, by saying that, I don't tell you how much I should implement this undersampling. So there is a question, so according to which distributions, which probability distributions. So if you do that naively, so you just spread uniformly the red spot here in your 2D case space, and with equal proportions between the center, which represents the low frequency, and the boundary, which represents the border, which represents the higher frequency, then if you do that, it doesn't work. So you don't recover, even using the right tools, the compressed sensing reconstruction, you don't recover your original image. So why is so? I will give you just the intuition, not the mathematical proof, of course. But it's so because if you restart from this wavelet decomposition of your brain image, you see this. So for those who are not familiar, so we have 1, 2, 3 decomposition levels, and in each levels, again, we have here these low frequency approximations, and here we have details according to the horizontal, vertical, and diagonal axis. And this is reproduced at multiple scales, okay? We start from this decomposition, we iterate here and there, and so on. And what's happening is that these details that you can see here in the detailed subbands are very high frequency. So, and most of the coefficients are almost 0, which means that you can massively undersample these components. You will recover them from the sparsity reconstructions, sparsity on force reconstructions. Okay? But this component is not sparse at all. It's a low frequency, it's the background of the image. So you cannot rely on the sparsity criteria to recover this part. So this means that these informations must come from the data, okay? Must be sampled on the data. And because this information is low frequency, you have to oversample the center of case space, which is low frequency as well, okay? To be sure to capture the right contrast, the right background, and so on. But in the periphery, basically, where you measure high frequency are more or less mapped to these detailed coefficients. You can drastically remove some information. Okay, with that in mind, when you now apply these toy examples by just picking up 5% of the samples, you recover this synthetic image. Okay, but I told you beforehand that in MRI we sample along trajectories, not pointwise. So how it's implemented in practice? It's implemented just by considering the original sampling trajectory and applying a variable density sampling either along a single axis, if you do Cartesian imaging, okay, centered along the central portion of the case space, or applying, for instance, a variable density sampling in spiral imaging with non-Cartesian trajectories. Okay, it works quite well. Last ingredient in compressed sensing is the image reconstruction step. So it's actually optimization problems, which basically will consist in minimizing the sum of two terms. So this is what we call a data consistency term. So your data are measured here. So this is a Fourier operator, okay? For instance, I show you a nice case space sampling patterns that I will detail afterwards. This is related to the sensitivity maps that are used typically in practice in clinical imaging by activating these parallel imaging principles. And you have here 8 sensitivity maps. Each of them is focused on a specific part of the human brain. And this is the data collected in the case space. And we have L coils, capital L coils. And this is the second term in the criteria, in the objective functions, that enforce the sparsity. For instance, it can be L1 norm or other regularizing terms. But it will control the degree of sparsity in this decomposition. And psi is typically the wavelet transform and other stuff. So we have developed tools to do that. And of course, you need to optimize this criteria. And this criteria being convex, you will end up with basically a single solution, a single optimizer. But because, of course, minimizing this cost function doesn't admit the closed form, it's iterative, it's very computationally demanding. Okay. So we will see solutions to overcome this issue afterwards. So what you need to retain at this time is that, okay, conventional imaging time, you collect full K-space samples, reconstruction is super fast, it's just applying an inverse fast Fourier transform. In the opposite, compressed sensing, you shorten the acquisitions, but you transfer the complexity to the reconstruction task. So you have long reconstruction times, also uncrafted sparsifying transform. Why choosing this instead of that one? You should compare the degree of sparsity of your image between multiple dictionaries. It's pretty, I would say, heavy and time-consuming and not really interesting. And you also need to set high additional hyperparameters, which is a bit painful as well. So in regards to the optimizations of the sampling pattern itself, so I'm going to show you how to basically go beyond this part. Just because this approach is just considering existing and analytical sampling patterns, just undersampling over the sampling patterns. But we can do much better. So let's go. So this approach is basically here a summary of, I would say, 10 years of efforts. Summarized, this is 4 papers. Sparkling stands for Spreading Projection Algorithm for Rapid K-Space Sampling. And I'm going to explain you as simple as I can, I would say, and don't hesitate to ask questions afterwards, how it works. So we have seen beforehand that MRI image is actually collected in K-space, but along trajectory. We can collect either Cartesian or non-Cartesians, but we know that non-Cartesian sampling is more efficient in the sense that in a given amount of time, you cover a wider K-space area. And we know as well that we should implement variable density sampling. Of course, we can implement VDS using spiral or radials, but if for any reasons I've given you an optimized target sampling density, which is represented here, given by this guy, pi, potentially what's going to happen is that this spiral will no longer be compatible with the hardware constraint that I talked about before. So to solve this issue, we basically invented these sparkling algorithms, which is a non-parametric optimizations of the locations, okay, of the red spot here in K-space, so which are represented by this capital K. And so the idea would be to cover entirely the K-space, but to match this, target sampling density while being compatible with the constraints. So you have this, that's why it's an optimization problem and under constraint related to the scanner. So what we are optimizing? We are optimizing basically a data consistency term again, but this time between your density, your target sampling density, and the positions of your K-space samples. And basically here it's a convolution. I won't go into too much details, but you measure the distance between this density and the position of your trajectories. And okay, but what might happen is that you put all your sample here and nothing, and no sample out of there. So of course you also need to make sure that you avoid cluster configurations or void space configurations. That's why we have also these terms. Basically, this is a repulsion terms that make sure that locally the sampling is uniform. Okay, and now the constraints. So the constraints, I presented you the constraints before related to the first derivative of the trajectory and the second derivative related to Gmax, maximum gradient amplitude and slew rate, Smax. So which means that we will have to be compatible to make this optimization subject to this constraint. Make sure that all the shots, all the trajectory elements, so the small k are just the elements, the shots of this capital K. And basically we can, because these two guys are differentiable. We can implement a gradient descent algorithm, okay, and we alternate this gradient descent with the projection onto the constraints. So won't go into more into details, but we have a proof of convergence of these algorithms. It's, of course, it's not convex, so because this is a difference of convex functions, but which means that it depends on your initializations. You won't end up with the same solution starting from a radial or from a spiral initializations, but you have this type of behavior, applying the gradient descent steps, so these first lines, transform the position of the points to something which is much closer to your target sampling density. And then, shot by shot, and even in parallel, you pick up the shot. As you can see, the shot is not compatible with the constraints because you have angular points, but you project, you smooth out basically the constraint. But this projector is consistent with the target sampling density. You don't modify the target sampling density by doing this projection. And so, so we ended up with implementation in 2D and implementation in 3D in GPU. So I won't give you the details, but it doesn't really matter. But 10 to 15 minutes in 2D, 6 to 10 hours in 3D. But you do that beforehand. So you basically compute your trajectory and then you put them in the sequence. So you don't need to do that online at the console. Validation at 70 for the 2D trajectory. So a Cartesian reference in 2-star imaging at almost 400 micrometers in plane. And we collected 11 slices in 4 minutes, 42 seconds with a Cartesian reference. And in-out sparkling in only 14 seconds with very compatible results. And in comparison, the radial and spiral competitors show very impressive streaking artifacts or signal void due to B0 inhomogeneities, for instance, or at least to undersampling artifacts. Now we move to 3D, and again we used Cartesian reference, already accelerated using GRAPPA, this time at 3T and 600 micrometer isotropic. 15 minutes and 13 seconds in terms of acquisition times. Here I show you comparisons between two 3D approaches, the full 3D that we finally implemented and promoted, in comparison with the previous attempts, which is a stacked version, a spherical stacked, but with a limited power of accelerations along the stacking directions. And as you can see, this guy provides much better images as compared to that guy. The images were reconstructed using exactly the same reconstruction strategies. Everything else was similar, so comparable. So same acquisition time and so on. Only 4 minutes and 48 seconds, and of course you can push further the acceleration factor. It was decent and reasonable in terms of image quality till an acceleration factor of 15, and then of course image quality was degraded. Okay, if I'm going to have time afterwards, I will explain you how to handle also this signal loss due to the B0 inhomogeneity artifacts, which are especially enhanced when you are doing non-Cartesian imaging as compared to Cartesian imaging. Anyway. Okay, we have also implemented sparkling for sodium imaging at 7 Tesla with a higher acceleration power as compared to twisted projection imaging, and doing that for fMRI as well with similar or even slightly increased statistical power in comparison with 3D EPI in fMRI at 70. And now we have also collaboration in angiography and perfusion imaging with Oxford. In regards to, for instance, just to insist on the complexity of the image reconstruction task, in regards to fMRI image reconstruction, I show you this workflow because it's really heavy at 70, because we also need to monitor what we call the dynamic B0 fluctuation, which are recorded by a scope camera, a field camera, and that allow us to transform, to correct for the baseline, the time varying baseline of the B0, plus the modification as well on the trajectory that we implemented. So anyway, just an illustrations to show you that in that framework, you need to reconstruct each and every volume in the scan sequence. And in the end, we did that, by spreading the reconstruction over multiple GPUs, and it took still 3 to 8 hours on a supercomputer, which is not doable for, I would say, the cognitive neuroscientist. So that's why there is a lot of demand to make this faster and so on and so forth, and this justifies the efforts we have done on deep learning afterwards. Okay, now we have seen how to accelerate the acquisitions. Now, in regards to the image reconstruction, I showed you the usual pipeline, and now we're going to move to the deep neural networks. So, before diving into specifically deep learning for MR image reconstructions, let's just make a brief introduction to deep learning. So the power of deep learning will be, of course, to be able to learn prior information from example, what we call the data-driven approach. And typically, I'm going to talk this example just by showing you. So the idea will be to map, to estimate a function f theta that depends on parameter theta that allows us to recognize this dog and label it as a dog. Okay. So f theta will be a neural network, which is basically a chain of elementary linear and nonlinear functions. Let's see a very simple example to illustrate that. So this is almost the most basic neural network that has been introduced in the literature. It's a multi-layer perceptron. And basically here you have the input of the network, so piece of the images, for instance. And in a neural network, you combine linearly these inputs, you sum them, and then you pass through a nonlinear function, which is called f here, and which can be a sigmoid, a nonlinear rectified linear unit, and so on and so forth. And your goal in the end, what it is to minimize this distance, okay, between the output of the network and the true label. Because initially, of course, this was developed for supervised learning, so you train your network with known labels, okay? And then, of course, once you have optimized the weights, once you have found the W here, then you apply to unseen data to see whether you are able to predict the right label or not. In regards to the imaging field, what has been very popular are convolutional neural networks, because they are implementing linear operations and convolutions that allows you to denoise locally the image. And if you combine this with operations like max pooling or average pooling, this allows you to analyze the image at multiple scales, basically. Somehow generalizations of techniques like Weber transform and so on. So, and in the end, you of course end up with a flattened layer that if you fully connect it, then you can basically predict the output, which can be here a discrete label, for instance, and with eventually assigned with a probability. So with this kind of tools, you can basically, and of course there are more recent developments in that field and transformer and so on, but I won't go into that details. But with this kind of tools, you can create deep learning architectures to do image reconstruction, and even other tasks in computer vision, as we saw yesterday, for instance, with Pierre for image segmentation and so on. So we have this training set composed of input xi and output yi, which lives in this space. We assume that these pairs are identically and independent distributed samples. And we basically try to estimate this function, this prediction function from x to y, by optimizing its parameter theta. So supervised learning will mean that we will try to minimize these cost functions. So again, here xi are the input, so the image. Yi is the label. The loss function here, it can be just a distance, a square L2 square measures, L1 distance, or anything you want, for instance, a cross-entropy measure. F theta is a neural network. What is important here is, of course, that we don't do that only for a single pair, but for an ensemble, capital D, and we average the results across all the pairs, which basically means we try to estimate an expected value in the statistical sense, and we minimize this confunction with respect to theta, so with respect to this guy. So how are we going to do that? So we need an optimizer, basically an algorithm that allow us to optimize. And we're going to use stochastic gradient descent as an algorithm, because usually in machine learning, you are not able to load all the data simultaneously, but what you're going to do is to subsample the data space and do gradient descent. And this is why we call this kind of algorithm stochastic, because you subsample the data space. And it has good convergence property, and there are some refinements in the deep learning frameworks, notably Adam or Rectify Adam and so on. And then you're going to use what we call the chain rule in terms of the computation of the derivatives. Basically just to, if you want to compute the derivative of your cost function with respect to y, but you can apply this chain rule. So going through x and derive x with respect to y and so on and so forth. And this is basically what you're going to do by derivative the function with respect to the output and back propagating the derivative up to the input. And this is already, of course, implemented in all development framework like TensorFlow, PyTorch, and so on. So what do you need? You need data, you need computation and memory power, and an implementation framework, like I said, for instance, now the most popular one is, of course, PyTorch. Okay, now with that in mind, we're going to see how deep learning has been used for MR image reconstructions. I'm going to try to adopt a general point of view, not restricted to this publication, which are hoarse, but to see you also the limitation of the field currently. I won't have time to cover every aspect. I won't talk about self-supervised learning, neither GAN or recent diffusion prior techniques, which are very, very nice, but quite unstable still at the time we are talking about. But what at least we can do a taxonomy, first taxonomy of existing approaches. So we have this image domain learning, which basically works from image to image. So you start from a zero field image reconstruction, and you try to implement a neural network in the image space. We're going to see what is done and what are the limitations of that. Similarly, you can do the exact same procedure, but in the K-space. You can implement a neural network in K-space, and once you have filled up your K-space, just do the inverse Fourier transform to reconstruct your image. And then you have two other competitors. Domain transform learning, basically you completely forget about the physics of the problem, and you try to map the K-space or any other acquisition space to the image domain. And finally, what we call cross-domain or hybrid domain learning. And this will be, I will spend most of my time on that at the end, because this is the most promising approach. So single domain learning, and we're going to start with the image space. So here, basically, what you're going to do is first, so you pick up your data, you apply the adjoint operator, so the adjoint Fourier transform, and so you have an aliased image, because this is a linear reconstruction from massively undersampled data, so you have potentially aliasing artifact and so on. And what you're going to learn is this guy to map the aliased image onto the true reference. Again, and this is a supervised setting, so you know in advance you have at your disposal reference images that were just undersampled at the time of the training time. So this kind of approach is simple and fast, but because the aliasing can be widespread, usually you will require a very deep neural network to eradicate the aliasing effect. And of course, people have started to use that, in particular the UNET, because it was originally introduced in 2015 for image segmentation purpose and so on. But for image reconstructions, people realize almost in 2020 that it's not the right approach, because you can produce some hallucination effect, in the sense that once you have removed the aliasing effect using your decoder and encoder and decoder decomposition, you can end up with some spot, for instance, or you can either miss some features or add synthetic, or I would say unrealistic features in the image that were not present initially. So there was a huge debate on that at this ISMRN 2020 workshops, and also more, this was formalized theoretically in this paper published in PNAS 2020 by Antoon and colleagues. This is a team of Anderson Sale at Cambridge in the Applied Mathematics departments. And basically, I will just show you these illustrations, but here you have the reference image, the sparse sense reconstruction, which is time-consuming and so on, potentially inaccurate, but at least you see the malign tumor there. And with deep learning, the tumors was almost erased. So, and this was used, this was obtained using UNET. So, and here it was another slice and good image quality. So, you know, on a given slice, the UNET produced the best quantitative imaging score, but eventually was not able to detect what matters the most, so the lesion. So clearly there are some dangers of using this kind of approach. Now, symmetrically, there is also the single domain learning in the K-space. So first you try to build up a deep neural networks in the K-space, and then once your K-space is completed, you will apply the simple inverse Fourier transform. So mathematically, this can be formalized like this. You apply directly a neural network, you learn directly a neural network on Y, which is undersampled data. And then once this guy is full, you will apply the adjoint operator to recover the image. This is somehow an extension of the GRAPPA technique that is very intensively used in the image in the parallel imaging setting. So except that GRAPPA is linear, so you can extrapolate data in the K-space using nonlinear convolution kernels. With GRAPPA, you have linear convolution kernels. So there are some approaches that learn from directly from auto-calibration data, but you don't know exactly how to control the behavior of the kernels, because you don't know exactly how the feature in the K-space are transposed into the image space. So it's questionable as well. But it works still quite well, because, for instance, in the Siemens package, which is called Deep Resolve, they have implemented denoising in the K-space and super resolution approach that allow them, at least in 2D, this works only in 2D, to save 50% of the exam time. Conventional exam on the left with a T2 weighted contrast, turbo spin echo, iPad factor of 2, which means undersampling factor along the phase encoding directions of 2. And here, basically, what they obtain is a iPad factor of 4 with Deep Resolve, with a 200 micrometer in plane resolution. But still, as you can see, 6 slices, because it's 2D imaging, it's not 3D imaging. Okay, now model agnostic learning. Model agnostic learning is basically you forgot about the presence of the Fourier transform to link, to establish the relationship between the X and Y, and you try to map directly these two guys. Of course, initially, this was introduced in Nature, in the Nature paper by Zhu and colleagues from the AGH at that time. but it can be quite appealing at first glance, at first sight. But actually, what people realize is that it doesn't scale at all. It worked only for 2D and not for 3D. And so this is, I won't go into details, but basically the idea is that really to find a low-dimensional embedding relating the sensor domain to the image domain and try to fully connect these two guys. And so you need fully collected layers in your networks, and that's why it's so computationally demanding, because you need to find the weight for hundreds of thousands neurons. But if it works whatever the undersampling patterns, whatever the forward operator, I would say, even for tape and so on. So you can do somehow some transfer learning, so learn for imaging modality and see to what extent you can transfer to another one. So in the paper, they demonstrated that it's quite robust to the different sampling patterns they used, and they showed very significant results and quite compelling and so on, with a very low error. But then, again, Colebrook and colleagues, still the same team from Cambridge, published a PNAS paper in 2022 demonstrating that this automap approach is not robust to noise, because you completely lose the structure of the image at a certain amount of noise. So in comparison, they proposed FireNet, which is a specific implementation of unrolled deep learning models that I'm going to present afterwards, that show a super good robustness to increased level of noise, as you can see here, even though, of course, you see a degradation of the image quality, but not completely a mess. So last type of approach is cross-domain learning. So cross-domain learning is a bit more complicated, and I will spend a bunch of time on that, because the idea is to really combine operations or corrections in the Fourier space and in the image space. At this time, it's basically the most promising and most interpretable results, because they are connected to the optimization field, optimization in mathematics. So we know, as far as we can, we know what we do. But of course, this is at the expense of additional computing time and repeated forward and backward pass between the acquisition domain and the image domain. So let's try to see how it works. And to try to give you an idea, we're going to make an analogy so between an optimization algorithm, so this guy, and the representation of the network as an unrolled structures. So again, the idea of this type of models will be to alternate, so correction in the image space and correction in the case space in the Fourier domain. If we restart from the optimization framework, typically for when we solve, and that's why I talked about the compressed sensing approach. In a compressed sensing reconstruction approach, you alternate a gradient descent step with respect to your data consistency, you L2 norm with respect to the data, and what we call a proximity operator step, which basically corresponds to the generalizations of computing a derivative for non-differentiable functions. Okay, and this alternating these two steps give you usually what we call a proximal gradient method, and converge to a stationary point. It's convex, it's well established. And now we're going to see how we can represent this algorithm into these structures. So to help you a bit, so I put some colors. So here everything happens in the case space domain. So you have this yellow block. The operator to move from one domain to the next are represented by this green square. So that embeds the Fourier operator and the sensitivity maps. And the image denoising happens potentially with deep learning networks, basically match these proximity operators. So as you will see, we're going to replace this type of operations that happens in the original optimization framework by something else that I will show you afterwards, based on deep learning corrections. Okay. And then this is just one iteration of the algorithm. This is just one layer. Here you can see one layer. But then here you see another layer because I replicate the same blocks, and another layer will correspond to another iteration. And that's why we call this unrolled or unfolded structures. Okay, let's try to make this game. I'm sorry, I don't have any questionnaire to but so we have these two equations that we can represent with this block diagram, and this means that it iterates. The idea here is to, oops, sorry. Okay, we call this step data consistency. We call that step proximal step, okay? And again, usually this is really the denoising step in the original optimization framework. And now we unrolled the structures. So we chain this data consistency and proximal step with the next one, and so on and so forth. And we repeat that process n times. We have n iterations. And now what we're going to do is to replace the proximity operator by a neural network, okay? That we're going to learn in the supervised learning setting I introduced before. So we're going to replace proximity operator by neural networks, and potentially with different parameters, which means that at each iterations, you're going to learn a different set of parameters. Because typically, once you have, for instance, denoised the image at a certain scale, then you will just see artifacts at a more tiny scale. So you won't need the same amount of denoising in the subsequent iterations. And so you have the whole network represented here. And so we implemented this kind of idea using doing a benchmark, and notably notably on several public data sets that were available in 2020, notably the fast MRI dataset. So initially the knee fast fMRI dataset, and afterwards the brain fast MRI dataset. And we compared several architectures. So zero field reconstruction is just the zero field adjoint Fourier transform. KikiNet is a network that alternates correction in k-space, in image space, but just only twice. UNet is what we see beforehand, so just encoder and decoder structures in the image space. CascadeNet is also a type of networks that generalize UNet, and PDNet is a primal dual networks that was originally introduced for computed tomography in IEEE transaction and medical imaging, and basically that will perform corrections not only in the image space, but also potentially in the acquisition space, so in the K space for us. And we showed that this PDNet outperforms the other guys. At that time, you have it's maybe hard to visualize this on this slide, but you see the residuals. Here it's flatter, less residuals. The code is available for the sake of reproducibility, if you are interested in, and even we uploaded the model weights and hanging face interface that allows people to benchmark their own model against what was proposed at that time. And now we added additional ingredients to make it better. So we transformed the original PDNet into XPDNet, X being like, you know, a joker. And we put together all these iteration units, and this is the original implementations. We actually concatenated multiple versions of the reconstructed image just to be able to learn these parameters, which is a step size basically. And this is one of the crucial ingredients that was outlined by Antoon and colleagues to make sure that your network is stable. So this is one of the reasons why it works quite well. And on top of that, we also changed the type of network. Instead of just using, for instance, embedding just a convolutional neural network here, we use the multi-layer wavelet convolutional neural networks. I won't go into too much details. And one key ingredient was also what we call the S-maps refiner, which basically allows you to improve the estimation of the sensitivity map coil by coil, okay, to make sure that in the end, the way you combine the information from the multiple sensors for the multiple coils is improved. And this is typically the way we proceed with that. You have your input k-space data stacked over the coil dimension there. You basically apply a mask over the central k-space line if you are doing Cartesian acquisition. If it's not non-Cartesian, you are just, for instance, doing small regions corresponding to low frequency because sensitivity maps are low frequency information. Then you go to the image domain by applying inverse Fourier transform. You denoise using a unit these maps, and then you reconstruct coil-wise each sensitivity map just by dividing by the square root of the sum of square. And with that, we compete on the 2020 Fast MRI Challenge, which was really an international challenge where 19 different teams were involved with a significant and very large data sets consisting of almost 7,000 brain scans and collected between 3 and 1.5 Tesla over 9 different machines. Approximately 1.5 terabyte of raw k-space data, and we participated in 2 different challenges, the 4x and 8x acceleration tracks. We did not compete for the transfer track, which was even more challenging because this was the challenge where you train your own model for a Siemens scanner and try to transfer to General Electric, to GE or Philips scanners. But anyway, what was pretty interesting as well is the diversity in this data set is that you have T1 weighted, flare imaging, but also T1 post-injections, post-gadolinium injection, and T2 weighted. And so after, so the evaluation was done first on quantitative metrics, SSIM, PSNR, and so on, but it was, of course, judged not enough. That's why a second round of evaluation was done by radiologists in a double-blind manner. So they didn't know what of course type of images they were evaluating for which team, I mean. And finally, we secured the second spot of the competitions with these XPDNet architectures, both for the 4X and 8X track. And the criteria were based on the amount of artifacts, the sharpness of the images, and the contrast to noise ratio. If you are interested in by just watching the summary of the challenge, here is a video in 2020 NeurIPS conference. And this is also summarized in these 2 publications, this one dedicated to the challenge itself. And so here is a typical example for the 8X track, where you see the ground truth, the XPDNet recon. Maybe I should turn off the lights. Zone 3. Okay. I don't know if it's better, but at least what you can observe is that you have flatter residual here. We have pretty good consistency between the ground truth and the XPDNet recon. it's maybe more difficult, both quantitatively and qualitatively, to reconstruct the flare images. SNR is a bit lower. And of course, the results were even better for the 4x undersampling factor. And what I would like also to show you is a comparison between this deep learning solution and the usual linear reconstructions that are implemented at the console on the scanner itself. And this is an example we did, still on the validation dataset, between our XPDNet record with these numbers, these figures, and the GRAPPA record. And at the acceleration rate, you see instantaneously the benefit of using this solution in comparison with that one. Here you can see the undersampling, the aliasing artifacts along these directions, because the undersampling was performed along that dimension. On top of that, in terms of reconstruction time, we were at 1/4 of seconds per slice, which is really decent and compatible with the clinical routine. This is a zoom showing you how close are these two images in comparison with the GRAPPA reconstructions. But now there is a huge domain of applications where non-Cartesian imaging is beneficial. We have seen that in cardiac imaging yesterday morning, but also in other applications, abdominal imaging, or even for brain imaging. If you want to go fast in fMRI, for instance, you might be interested in doing spiral and so on. So we have, we have implemented actually recently a new open source package called MRI NUFT. It's both a benchmark of multiple backend of the non-uniform fast Fourier transform, but also a package that allows you to evaluate the performance of multiple sampling patterns. So it works in 2D, stacked version of 2D to access to 3D imaging protocol, or rotated, conical, 3D cones, TPI, and also 3D sparkling Howard stuff that I showed you before. And with that, we have also extended the original XPDNet or PDNet to non-Cartesian imaging settings. We still kept the same and similar architectures as before, except that this time we introduced a very instrumental guy, which is called density compensations. And density compensation mechanism is something known from the late 90s. It was originally introduced by Pipe and colleagues when they started non-Cartesian imaging, to realize that if you collect more information, more samples in the center of K-space at the reconstruction stage, you should basically downweight this information in comparisons with the high frequency, because they are more numerous. So you should restore somehow a balance between the low frequency information and the high frequency information. So you have multiple strategies to do that. Some are based on Voronoi diagrams and so on, but whatever. And so we have implemented this guy within our deep learning setting. And we have shown in 2D and 3D that this is a key, especially in benchmark. This is a key to reach higher image quality. So this is an illustration for 2D single coil fast MRI in imaging, both radial and spiral. You see that whatever the techniques, spirals provides an average, maybe better image quality. And what is interesting is that if you compare the different approaches, so this is a reference where we, for instance, we use a gridded PDNet. What does it mean? Gridded means that we actually projected onto the gridded onto the grid in the Fourier domain prior to applying the usual PDNet, and we obtain somehow similar artifacts as here, like doing adjoint or like using UNet. So because UNet is applied on this output, so you observe still some aliasing artifacts. So NCPDNet was really instrumental in removing these artifacts and being really closer to the reference. So just to illustrate how important it is to stay in the continuous setting with the non-uniform fast Fourier transform and implementing this density compensation mechanism. Okay, we generalize that, of course, to multi-coil imaging with as you are in multicol, you have a higher SNR. So with a higher SNR, you end up with improved image quality score. So SSIM and radio and SSIM and PSNR. Interestingly, also is that this NCPDNet network basically is much cheaper in terms of numbers of parameters as compared to the UNet, and this is consistent and compatible with what I said originally with this image domain reconstruction techniques that basically needs a lot of layers to correct, to eradicate these issues. So in 3D, we played with the OASIS dataset, and we obtained quite a decent result, even though at that time the model was trained on a V100 GPU board, and now we can do much better with A100 because the amount of memory available is 80 gigabytes instead of 32, but it was pretty convincing. Okay, so okay, it's 5:50. I guess that you are not completely dead, but maybe I'm going to finish this, and if you want, we can make a short break before the last part. So what I would like to tell you here is that there is a classical issue, notably in non-Cartesian imaging, and a classical issue in MRI, which is called the off-resonance effects, and which is produced by the spatial B0 inhomogeneities. These B0 homogeneities are due actually to local fluctuations in magnetic susceptibility at the interface between tissues and air. So there are some gradients of magnetic susceptibility over there, so near the sinuses or near the ear canals, okay? And when you are doing Cartesian acquisitions, this effect, basically, if you add artificial delta P0, for instance, so this effect has consequences, detrimental consequences on image quality, but basically only along the readout direction from left to right, yeah, okay? But when you are doing non-Cartesian examples, because you are integrating at least over 2 or 3 dimensions, then adding this delta B0 is very produced not only what we call geometric distortions, but also blurring effect and even signal void. So that's the key reason why most of people in MRI don't want to do non-Cartesian imaging, because it's very sensitive to off-resonance effects. So how do we solve this issue usually, if you have time, if you are a bit ingenious and so on? So basically the usual ingredient is to leave the idealized Fourier acquisition models that I presented to you initially for a more complex extended acquisition models, where you basically take into account this guy in red. So this is an exponential complex term that relates the object to be image, f of r, to the signal that is measured, s of t. And this term is basically related to the resonance frequency of Cette, omega of r, which depends on the spatial position r, and which is directly proportional to the delta B0, so basically the spatial fluctuation of the static magnetic field. So we have some techniques to solve this, but we will see that it's very computationally demanding. Why this guy makes the reconstruction problem difficult? This guy makes the reconstruction problem uneasy, I would say, because we have these terms. This is a discrete formulation of the previous equation. But these terms basically depends simultaneously on the frequency, which is indexed by the space, okay? Because the Larmor frequency fluctuates here as a function of space, and the time evolves in the K space. So index m is in the K space, index n is in the image space. And the classical solution, the most elegant solution that was introduced in the field almost 20 years ago, is basically to perform a polynomial expansion to break down this simultaneous dependence, okay, as a product of variables, B, M, L, and C, L, N, and a summation of product over a number of interpolators, capital L, where you basically split the dependence with respect to the k-space for B and the image space for C. And if you do that, if you replace this guy by this sum, and you invert B and C, you can immediately identify that your collected signal, S, is actually a weighted sum of non-uniform Fourier transform. Okay. And if you are able to estimate these parameters, B and C, and this can be done typically if you have collected this information here using a separate acquisition, and we will see how to do that afterwards, you can perform a SVD, so singular value decompositions, typically to estimate these two matrices, B and C, and perform minimize this L2 norm. And once you have done that, you are able to compute the forward operator and this adjoint. Okay, nice. And if you do that, in comparison with the uncorrected reconstruction, which is here, represented here, you can collect additional information, so through an additional scan, an additional sequence. So this is time-consuming and so on. But you can do that, for instance, at a resolution of 2 mm instead of the native acquisition here of 0.6 mm isotropic, with multiple echo time to have a nice estimate of the delta B0. Then you end up with a very pretty decent images in comparison with that. So what we showed last year and the year before even, is that with the sparkling data, we no longer need of a separate scan to estimate the delta B0. We can extract from the phase of preliminary reconstructed image the information related to the spatial inhomogeneity of the B0 field, and then inject it in the same recipe, in the same model for reconstruction, and recover the signal loss. And this is reproducible across subject, of course. And this happens at different locations in the brain. Yes, this is nice, but so we did the cover page of the issue of MRM, but anyway, it's 8 hours of computation. So here it's another illustration of why all this stuff of compressed sensing in a very high dimensional setting and so on is not compatible with the clinical routine. So why did we do to handle to solve this issue? What we did actually is that we picked up the previous non-Cartesian PDNet implementations, but we transform the data consistency originally, which was only based on a Fourier model, with this extended model with the guide that I presented you before. And of course, if I just replace the model because of this complexity, I won't gain anything. So the questions we handle and we solve is that how can I approximate this operator by reducing the number of interpolator, reducing the number also of channels, of codes involved in the reconstruction and so on, and eventually reducing the number of iterations enrolled in the network itself. So we train multiple models, multiple extension of this NCPDNet to solve that. And what we showed is that with a network defined over only 5 iterations, 5 interpolators, and with the call compressions that involved in the end only 5 different data sets, we basically train all these neural networks, and we show that we were really close to the reference, which was reconstructed in 8 hours, the reference that I showed you before, the compressed sensing solutions implementing the full polynomial expansion in the data consistency term. So we have only 225 calls to the non-uniform Fourier operator instead of 15,000. Okay, and if you do that, you have you have a huge gain in terms of reconstruction time, because instead of 8 hours, you end up in 7 minutes. But why it was important to perform this operator compression or operator approximations? It was important because if I if I use the neural network, the NCPDNet, but just with the classical data consistency term, what I obtain in this area is just a blurring. So it's completely non-consistent with the original reconstructions. So really, writing and involving the right forward model was critical to save time and to be accurate as well. So that's what we did to handle that. So to summarize, so now I would say that deep learning is mature for MR image reconstructions, at least in the supervised setting. It provides improved image quality at lower computational cost and robustness to various imaging contrasts, especially we saw that with the fast MRI challenge. Robustness also with respect to SNR, field strength, and so on. Somehow we still need to train different network architectures, at least in the enrolled learning setting, if you are working for different acceleration factors. And now there is this FireNet architectures, which is eventually able to be both stable and also accurate. So our solution, so yeah, I was wrong second, but whatever. And what matters is that most stable solutions must be informed by the physics of the problem, okay? And can work for non-Cartesian sampling in 3D and correct off-resonance effect and so on. What I didn't discuss today is all this recent self-supervised and zero-shot learning approach. Some of them are promising. The data augmentation mechanisms that should be used, and it's really important, in particular if you are interested in doing self-supervision and so on. And I would recommend to look at the paper, to read the paper about data crime published by Efrat Chiron last year in PNAS. Because what's happened is that in many papers in this field, people don't do the right stuff. So, okay. And so, for instance, there is a well-known issue, which is training your models with magnitude-only images, okay? MR images natively are complex valued. You have information in the phase as well. And even for some specific diagnosis, my colleagues who are neuroradiologists are interested, for instance, in what we call SWI imaging. SWI are susceptibility-weighted imaging. In SWI imaging, you have a specific processing of the phase informations to enhance notably the microbleeds. And this is critical to establish the right diagnosis, in particular when the spots are tiny and so on, when it's not a massive lesions, a massive anomaly in the image. So I didn't discuss that, but I encourage you to read that paper if you are interested in, of course. And I didn't discuss this generalized adversarial network, variational encoders, which are basically allow you, which are generative approaches to produce images or diffusion prior. It's a very recent trend, and we don't have yet a very global visions about their full potentials, because they have emerged in the machine learning community, but with not really significant validations on real and clinical data set. Okay, and okay, it's 6, so I can stop here, or if you are still courageous, I can talk about the last portion of my talk. Up to you. Tell me. If you are tired, we can stop there and make a break. And take questions, maybe. Up to you. Yeah, there is a run table. Okay, so come next year. Okay, so I won't talk about that, but the last part was about, so just to give you just in one sentence, so I presented you how to accelerate the acquisitions with, I would say, classical technique, and then how to perform deep learning for image reconstructions. And now we can merge both, okay? And this is what we developed there. We basically picked up in sparkling the best ingredient of sparkling and injected them in the deep learning setting to be able to train both the trajectory, the sampling trajectory, and the image reconstructions. And that's it. So I'm just finished with thanking all my colleagues and so on. Okay, so acknowledgements. Thank you to all these guys. So all these guys and all these colleagues contributed somehow to this result. So really grateful to them and you for your attention. And I hope that you are not dead. Thank you.